algebras, I'm not going to be talking about the whole continuous combinatorics, and even inside flag algebras, I'm not going to be talking about everything. I'm going to be talking about the semi-definite method. There's this nice picture that I like to draw about this continuous combinatorics stuff, in which you have all these topics, and they're organized into how finite they are and how infinite they are, these objects, whether they are more synthetic or algebraic, or semantic or more geometric. And flag algebras is towards the synthetic side. Today we're going to be talking about the basic theory that comes from the finite world of convergence sequences and flag algebras. And as I said, flag algebras actually has semi-definite method, inductive arguments, differential method, and other things as well. And we're going to concentrate on the semi-definite method, which is perhaps the most famous part of flag algebra. Okay, so I would like to start with the motivation, which is Mendel's theorem. So Mendel's theorem is this theorem here. It says, well, the maximum number of edges in a triangle-free graph is this number here, so roughly n squared over 4, attained only by the complete bipartite graph with balanced parts. So about n over 2 vertices on each of the sides and all edges in between. Now, there are beautiful proofs of this theorem, very simple proofs. I'm not going to do the simplest of proofs, but I'm going to do a semi-definite method proof of flag algebras in disguise, and then we'll see how this generalizes to, well, arbitrary theories that we're going to use from logic and model theory. Now, this flag algebraic proof that I'm going to do, even though you can retrieve the full Mendel's theorem from flag algebras, I'm going to do kind of a defective version, and I'm only going to prove this asymptotic version that says, well, I'm not going to prove n squared over 4. I'm going to prove about that, so meaning that the maximum edge density is about 1/2 plus something that goes to 0. And I'm not going to prove that this is the only extremal configuration. I'm just going to say, well, extremal configurations look like that. Okay? So here's how we're going to prove this. And it's going to be apparently a proof by picture, but not exactly. So we are interested. Okay, so first we have the trivial lower bound, which is if you just compute the number of edges on this guy, you see that it's this. So that gives you the easy bound, the lower bound. So flag algebra is going to be proving the hard bound, saying that you cannot attain edge density larger than 1/2. So we're interested in edge density. So let me write this to say this is just the edge density on my graph, right? Now, what is the edge density? The edge density is you pick 2 vertices uniformly at random and compute the probability that you see this picture, right? Now, another way you could say is, well, let's do this in 2 steps. Instead of picking 2 vertices uniformly at random, let's pick, and when I say 2 vertices, I mean a set of 2 vertices, not labeled, not ordered vertices, just 2 vertices. So let's pick instead in 2 steps, let's first pick 3 vertices, and out of the 3 vertices, let's look at what's proportion that we have of edges. If I do this experiment, I know that the edge density can be rewritten like this. So I can say, well, I could see the empty graph, I could see the complement of the 2 path, I could see the 2 path, and I could see the triangle, and each of them has a contribution. This one has no edges, so it contributes 0. This one has 1 edge, so it contributes 1/3. This one has 2 edges, contributes 2/3. And this one has full edges, contributes 1. However, our graphs are triangle free. So this one actually doesn't really appear, right? So that's another expression for the edge density, okay? Okay, so the next step that we're going to do is we're going to compute.
You don't care here about permuting these vertices?
No, because when I say I pick 2 vertices or I pick 3 vertices, what I mean is I pick uniformity at random, a subset of size 3. So if I take a subset of size 3, this says, what is the probability that I see a picture isomorphic to this?
Okay, so the isomorphic is...
Yes. Okay. And then every time I see a picture isomorphic to this will contribute 2/3 to the edge density, right? In 2/3 of the times that I pick a 2 subset inside there, I will see an edge, right? Okay, let's do a slightly different calculation. Let's fix some vertex V in our target graph. Maybe I should call this target graph. And let's compute, I could compute now some sort of fixed density.
What is a target graph?
The target graph is, I'm trying to prove that the graph, any graph that's triangle free has edge density at most 1/2, plus some small error, right? So fix one such graph.
Oh, so that's the graph given.
Yes, exactly, right? So I could try to compute edge densities that look like this. What do I mean by this is V is fixed, and I'm going to sample only the other vertex and ask what's the probability that I see an edge. So essentially what I'm computing here is the degree of this fixed vertex V, but I'm normalizing because I'm picking uniformly at random. So it's the normalized degree actually that I'm computing. But I'm not interested in this exactly, I'm interested in the square of this density. So let's compute the square of this density. And again, I'm going to do the same kind of trick and I'm going to say, well, I could think of sampling 2 vertices, right? Instead of sampling 1 vertex and multiplying these densities twice, I can think of sampling 2 vertices. And what I see is that, well, this thing is just the product of 2 densities. So I need to see some picture. If I'm sampling 2 vertices, I need to either see a picture that looks like this, or I need to see a picture that looks like this. And both of them contribute 1. But then again, our graph is triangle free, so this doesn't actually appear.
What again?
Wait, let me just. So if I want to compute the square of this density, I'm sampling 2 vertices uniformly at random. Potentially they can land on the same vertex.
Shouldn't you have in this picture like a V and a U, like 2 squared vertices?
Yeah, there are 2 extra vertices because this thing is the square of a density, right? So it's the product of 2 probabilities. You sample U1, you sample U2, and you ask, what's the probability that U1 gives you an edge times the probability that U2 gives you an edge, right? So this is morally the same as sampling the 2 vertices and asking to see either a picture like this, or a picture like this, or a picture that accounts for collisions. But the pictures that account for collisions are negligible, right? If you consider 2 vertices, the probability that if the target graph G is large, the probability that the 2 vertices were sampled to collide goes to 0 proportionally, right?
When you in the left hand side, you just sample 1 vertex and you square that.
Yes, it's the density squared. This is a number that is saying the normalized degree squared. Okay. But because I'm squaring it, I can think of I sample U1 and I sample U2 and I take the product of the 2 probabilities. And I can think U1 and U2 are picked independently now. And now it's a joint probability that U1 gives me an edge, U2 gives me an edge, right?
So how do you see that in one diagram?
In this diagram, I'm sampling both U1 and U2, right? If they don't collide and I see this.
So why do you have only 1 square of a
no, they are all, you just fix V. V is fixed. You just ask about.
V is not picked at random.
Yeah. Later you will have a result V, but you just fix V. You want to know it's the degree density. It's the degree density square.
The one that is sampled is not the one with the square, it's the other one. Yeah. Okay. Now it's.
And there's a small contribution accounting for the fact that, you know, the 2 vertices that you're sampling could collide, but that is negligible. Okay. Here's a similar computation. If you take the non-edge squared, you're going to get this plus this. Okay. And finally, you can also compute the product of these 2 guys. And this is slightly more complicated. You can have this or this. Now you have a contribution of 1/2 for each of these, because when I'm picking the product of these two guys, I'm thinking that, you know, I'm sampling U1 here and U2 here. These are ordered now because when I label this as U1 and U2, I need to, when I see this picture, I need U1 to be this vertex. It cannot be the other way around. So this only contributes 1/2 to that, right? So these are just simple computations.
Why don't you have half in the previous row?
This one, because both of them look the same, right?
Maybe it would help you using these diagrams to represent actual sums, right?
Well, it's densities, it's probabilities, right?
Maybe it would help if you wrote down what these represent
Okay.
like more formally.
Sure. So for example, this guy, this is the probability that when I sample a subset U contained in V of G, well, I guess probability U and V of G with size of U equals 2, that G restricted to U union V is isomorphic, well, with the special label on V is isomorphic to that picture. That's what I mean by that picture.
Very suggestive.
Yeah. Okay. Is everyone fine with this computation? Because now magic is going to happen, and then the proof is going to come out, and we're essentially done at this point. So here's how the proof ends. Well, I have the edge there, right? Well, I guess there's one more computation I need to do, which is I'm going to average some weird computation, which is, well, first I'm going to compute this guy. Take the edge, the special vertex, minus the non-edge, and let's square that. Well, if I square that, I'm going to get exactly this. Minus now notice that the 1/2 goes away because there's a 2 comes from the square, right? And now what I'm going to do is I'm going to say, well, what happens if I average over the choice of vertices? These densities. Right, so this, and I'm averaging over the choice of vertices. Well, now I want to write in terms of densities that do not involve V, right? So to see this picture, I need to see something that looks like this, right? In the original graph. And when I'm averaging over V, if I'm going to pick V afterwards, this, every time I see a picture like this on 3 vertices, it contributes 1/3 of the time to seeing a picture like this, right? Just think you're picking 2 things at random. This averaging, you can think that you're picking V at random, right? So here you're saying, first pick V at random and then pick the other 2 vertices. But you can flip the order and you can say, first pick 3 vertices and then pick V at random, right? This, every time you see 3 vertices like this will contribute 1/3 of the time to seeing this picture. Every time you see a picture like this, it contributes 1 to that picture. This contributes 1/3. Then you have minus this, it contributes 2/3. And you have this one. Also contributes 2/3. You have this small error. Okay.
So when you count the contributions, is how for picking those 3 vertices, how many options I have for arranging this graph? So that's the isomorphism, the number of isomorphisms for those three vertices.
Yes, so again, this you can see as pick V uniformly at random and then pick two new vertices after V and ask what's the probability that you see this picture. In here, I'm doing the thing the other way around. I'm first picking three vertices and then I'm picking V uniformly at random inside them. And then you can see that for example, if you concentrate on this averaging of V of this picture, every time I sample three vertices and I see this, it contributes exactly 1/3 to seeing this.
So the 1/3 means that I have only one out of the three vertices for which I see that picture.
Yes, because you're picking V and you're requiring that V lands on this guy. Well, V could have landed here, here, or here. These two do not yield that picture, right? So it's 1/3. Okay.
On a high level, you are trying to estimate the edge density, namely this edge.
The high level,
it's in pictures, things that are happening a lot. You condition on something like this V. You study a particular vertex, and then by averaging over all vertices, you lift the name you picked for that vertex. And relating that to it, it's just one step.
Yeah, no, I was trying to. The low level, not the high level.
Okay, well,
So
it's good. The high level is also.
Okay, so now we're going to use the fact that, as previously asked, this is up to isomorphism, right? If I have two isomorphic pictures here, I can collect the coefficients. And I have a lot of isomorphic things, right? These things are isomorphic. This guy is isomorphic to this guy. So I can collect them. And when I collect them, I see this interesting thing, which is now I have some negative values. Okay, just collected the isomorphism. There's still the error term. Okay. Now comes the final step of the proof. So we were interested in upper bounding this edge density, right? Well, whatever this number is, it's certainly less or equal than if I add the average over the vertices of that square. Okay. So I'm going to actually do small adjustments, and I'm not going to add the square of the thing. I'm going to add 1/2 of the square of the thing. And what happens when I do that? Well, I have the edge density.
There's a crucial thing here. The square is positive.
Yes, so this is a square. So whatever this number is non-negative. I add a bunch of non-negative things, so this inequality holds. And it is crucial, indeed. It is crucial.
The semi-definite method is a positivity.
Yes, exactly. We will see what semi-definite has to do with that square later on. Okay, so this is certainly true. This inequality is true. But now I have an expression for the edge density based off of densities of 3 points. And this is written in terms of densities of 3 points. So let's collect the terms. So I have 0 of the empty graph plus 1 times here, but there's a 1/2 there. So I'm going to get 1/2 times the empty graph plus over there, the complement of the 2 path, I have 1/3 there and 1/3 here, minus 1/3 here, but I have a 1/2. So this is 1/6 of the complement path plus the last term, which is the 2 path. I have 1/2 of the 2 path. Let's check. It's 2/3 minus 1/6 because there's a 1/2 there, right? It was a small error. Now here's the other inequality. It almost looks like 1/2 times something, right? But there's this 1/6. But I can just complete that because whatever this density is, it's a non-negative number, it's a density. So I can just add a little bit to make it 1/2. So this is just this. Okay. So now here comes the final step. What is this number? You sample 3 vertices and you compute what's the probability that's either isomorphic to this or this or this. Well, there's only one picture missing, which is the triangle, but I know that I don't have triangles. So this number is 1. I guess I'm missing the O1 everywhere.
It doesn't matter, we forgive you. We know that there is O1 everywhere.
Well, there's a reason why I'm forgetting the O1 everywhere is because when you go to the limit, this O1 doesn't exist. Okay, so we have just shown the upper bound, right, by some algebraic manipulation. And that's where the algebraic and synthetic part of flat algebra is going to come into play. You're going to do manipulations with densities. Now, I'm still missing one part of the proof, which is I promised to show that this maximum density is attained only by things that look like a complete graph, right? So let's prove that. And that is everything that I'm doing here is actually part of the semidefinite method of flat algebras, even this part where you try to extract some extremality condition that you say, well, if you have a guy that attains the maximum, then what does it look like?
Oh. Yeah.
Yes.
The intuition for the proof that you just saw will come later when you abstract it.
Yeah, unfortunately, most of the semi-definite proofs do not have intuition. You just, as you might expect from the name, there is a semi-definite program underlying the thing, and then you plug it in and it spits an answer. Now, sometimes there is an intuition which comes from this extremality part that I'm going to do, that you can gauge what kinds of things you should add to make this proof work. If you have an idea of what the extremal object should look like, based off of the second part.
Okay, so I should think of like the second step, like trying to estimate my thing, adding a semi-definite thing, then
Yes.
not the flow.
Well, adding something positive, and in our case, we added a square. The semi-definite method only adds morally squares, or sums of squares to be more specific. But in fact, you could add anything that's non-negative, right?
I should think of what happens later as like an ad hoc computation that happens to work out for the semi-definite program.
You can think of it this way, but there are ways of guessing what squares do you want to add, and we will see how the structure always looks like this. You start with whatever you want to upper bound, you add something that's typically some sum of squares, then it becomes a sum of things. You want to see what's the maximum coefficient that appears on that, bump all coefficients up to that, and then you get whatever is the maximum coefficient. That's how the semi-definite method will look like, at least the first step.
My goal would be to cancel out somehow the part.
Yeah, the idea is that if you look at the expression that I just erased, which was for the edge, there was a 1/3 of the complement of the two path, 2/3 of the complement, 2/3 of the path. This 2/3 of the path was the problem, right? Because if you just take the maximum of the coefficients, you would get 2/3, which is completely useless. So the idea is that you want to add some sort of squares, and the magic that happened is that this guy has some, even though it's a square, it has some negative coefficients, right? And that cancels the 2/3 and puts it down to 1/2, and that's how the proof actually closes. But unfortunately, this is the maximum intuition that you can get, that, you know, there are some magic numbers that cancel out, and then you get the proof. That's why it's synthetic. You know? If you want some more geometric kind of intuition, you need to go to the other side of the picture.
I guess you can give a tiny bit more intuition just by saying that you add only things that you know that in the external case should be 0.
That's the second part. That's exactly the second part. We're going to use this proof to show that whatever happens to extremal guys, everything needs to be equality. So this is the intuition of things that you should add if you don't want to lose anything. And if you want to prove a tight bound, you cannot add anything that in the extremal is not 0, right? So let's see the second part of the
But
proof.
maybe about the first part, just to worry, this is morally one of the proofs known of Montel's theorem,
Yes.
not in this formulation. So people discovered it. They do, you know, they do average degree, they do Cauchy-Schwarz, they do something. How they came up with it. Yeah, so this somehow, you know, abstracts and, you know, formalizes a method that You know, maybe you can automate, let's say, for discovery.
What?
You can maybe automate to discover.
Yes. The beauty of the semidefinite method, as we'll see, is that you can put this into, you can program something and then say, find me bounds for this problem. Now, granted, it's not always that it finds good bounds, but there's a vast amount of natural problems where this just closes the problem, which is quite impressive. Now, I also should point out that, as I said, there's a much simpler proof of Montel's theorem than this. And if you want a hint, try to prove that non-adjacency is transitive in an extremal guy. That's a very easy proof of Montel's theorem, and more generally of Turan's theorem. You can prove it like this, and it's much shorter than this. Okay, so let's go to the second part of this. So extremal G have equality throughout. Right. So let's look at these guys. Label these. So I have these two inequalities, and if I'm dealing with extremal G, the edge density is 1/2. The final part of the proof is 1/2. So everything is equality up to the error term. But I'm going to ignore the error term. Right. So what happens with equality on Chu? Well, what happened on Chu is that I added a small coefficient times the complement of P2. So this means that for G, this density must be 0. Right? So what I'm going to show is that this implies that G is almost bipartite. So what I mean by that is that if H has an odd cycle, then the density of H in G is 0. So G, not 0, small O of 1. And this is what I mean by almost. I'm not going to prove that G doesn't have any odd cycle. It's just that it has a negligible amount of odd cycles. Okay, so I might as well say that this guy is actually triangle free because G is triangle free. So if H has a triangle, then that density is 0. So I might as well assume that. And here's a small lemma. With H that looks like this density is positive. If I look at the complement of the two path in H, it must appear in H. And here's a proof by animation. So here's H has an odd cycle, right? So let's start the odd cycle of H. So I have at least four vertices in this odd cycle because it's triangle free. Well, H itself is triangle free, so this thing must be a non-edge, right? As does this thing. This thing also needs to be a non-edge. Well, now if I look at these three vertices, if this is also a non-edge, I see a copy of this, right? So let's assume there's a contradiction that H doesn't have that. So this must be an edge. Well, but this was an odd cycle, so this means that this odd cycle goes on, and again, H is triangle free, so this is a non-edge. So the odd cycle doesn't close here; it goes on to here. But then this is a non-edge, and then again you look at these three vertices, and this must be an edge, and then you need to continue this cycle and so on, and then there's a contradiction because the cycle goes on forever, right? You can repeat this arc. Okay. Everyone follow? Because it's a proof by animation. I can rewind the animation if you want. Okay. Now, how do I prove that PH of G is small of 1? Oh, I guess this is also not 0. This is O of 1. That's where the O of 1's going to go. Well, it's like this. Well, whatever is P note that this guy is certainly at least, I could try to find H and G. And then inside H, I can try to find this guy, right? The edge density is certainly at least that. The edge density, the density of the complement of two paths is certainly at least you sample something of size of H, check whether it's equal to H, isomorphic to H, and inside H, find something like that. Well, but this guy is greater than 0. And this guy is O of 1. So therefore, this guy needs to be O of 1. Right? So that finishes it. Right? Okay. The second part that I want to say, so I proved that it's almost bipartite. Now let's prove that's almost balanced. Now at this point, you could say something of the order of, no, it's almost bipartite, apply removal lemma, now it's bipartite, and then you can just do an optimization and find that the best thing you can do is n over 2, but let's actually keep to the spirit and do everything from the flag algebraic proof. And here's the final part. What happens if you have equality on 1? Well, equality on 1 gives me that for G. What did I add? I add that square, right? So what I have is that this average there's 1/2 here, but it doesn't matter. Is small, right? So again, equality says that everything that I did is tied up to these small errors. But this implies that, well, this is a sum of squares. So the only way that this thing is small is if most of them are small. So what you actually can prove is that for all but small o of size of G vertices, you have versus V. You have that this density is equal to this, except for some small error. That's the only way that this is going to hold. And then you're done, because now this is saying that it's almost balanced, right? Okay, so this, as the questions already suggested, there is a semi-definite program underlying all this, and we're going to see how that works in general. We're going to do this in general, not only for graphs, but for more general combinatorial objects. So let's go.
What is semi-definite program and what is flag algebra?
Well, we're going to see. We're going to see what this is.
Leo, I don't know. You just didn't say in the beginning. I mean, the originator of this theory and.
Oh yes, I should mention that. This is
basically given that you was your advice.
Yes. I should have. Should have pointed out that, in fact, everything that I'm going to present today is. Flag algebras. Curious fact, Mento's theorem is from also 07, but is 1907. So what is the first idea of flag algebras is to get rid of these annoying small o of 1 terms, because as you've seen, I forgot them a bunch of times, and the reason I forgot about them is that they don't really matter, right? If you're really interested about in densities or the leading coefficient on this function, right? So the leading coefficient when you're computing edges is going to be whatever is coming with n squared. You don't care about lower order terms. You might as well get rid of that O of one term. And the easiest way to get rid of that low O of one term is to actually build, well, not the easiest way, but perhaps the cleanest way is to come up with some sort of limit in which these error terms, they just become zero, right? So that's what we're going to do.
I can tell a story. So Sasha Razborov was here at the Institute when he started out with this. And he told me, I'm reading this extremal combinatorics paper, and this poor guy worked so hard to control the little epsilons, which are the little ones.
Yes.
Well, clearly they should look at that.
Yes. Okay. So, and we're going to do things in general. We're going to use these things of model theory. So again, people in the Zoom call can find these things in that website. It's up there. But here's the setup. We're going to have some first order language. So this is L. So it's a first order relational language or finite relational language.
Maybe it would be good each time when you say such a notion, say the special case for graphs.
Yes, I will. So I would just say a bunch of terms here, but let's focus on graphs, and I will write what these things are for our particular case of graphs. So bear with me for a second. So finite relational language, this is just a set, and each P in here has an arity. So this is, I'm going to denote by KP, is just a positive integer. And this finite relational language allows me to talk about L structures.
It's a relation, it's a number of parameters to the relation.
Yes, arity. So when I define L structures, it will be clear what do I mean by arity. An L structure, it has a vertex set, denoted by V of M, and it has a KP array relation EM, which is, well, it's a KP array relation, so is a tuple, is a subset of tuples of length KP of vertices, right? For each, so for each in my L, I have one such relation. Now, not going to get exactly
satisfied by the code.
Yes, I'm not going to get exactly into details exactly what is a theory.
This is the analog of what we draw there with the three vertices.
So we will get there, not yet. I'm trying to encode what will be my combinatorial objects. One of these choices will give me graphs. Actually, there we're not actually working with graphs. We're working with triangle-free graphs, which is a slightly different choice. It's similar, but it's different. But you have several other choices like hypergraphs and etc. that you also encodes here, and everything of flat algebras will hold in this generality. You fix a family of combinatorial objects that can be encoded like this, and it will hold. Okay, so this is an L structure. So you have some theory T, so first order theory T. This is just a set of axioms. And the model of T is an L structure satisfying these axioms. So let me give you the example that gives us the theory of graphs. So T graph, theory of graphs. So in this theory, the language has a single predicate symbol E. The arity of this predicate symbol is 2. And the idea is that we want this predicate symbol to encode adjacency. So if it's going to encode adjacency, the axioms of the theory should be, well, and I'm thinking about simple graphs. So I'm going to say, well, if you give me a vertex, then it's not adjacent to itself. And if you give me two vertices, if X is adjacent to Y, then Y is adjacent to X, right? And then you can see that the model of the graph is nothing more than just a graph. Right? Because what is a graph? A graph is a vertex set along with a binary relation, and the binary relation is irreflexive and symmetric. Right.
So here, when you said every X is drawn out of what?
Vertices.
But
All
where are the
vertices.
vertices?
Yes, because it's a first order theory, I didn't get too much in details. Quantification is always over vertices, not anything above.
But we always has an implicit set of vertices in the background?
Yes, because whatever the model is going to be an L structure. An L structure will have a vertex set.
Okay.
So here, notice the theory is not the graph. Models of the theory are the graph. Okay. So the theory is just saying which kinds of objects are combinatorial objects of this type, right? And here, if you use this theory, the combinatorial objects you're getting is family of all graphs, right? But notice that yes, undirected. Undirected here comes from this, right? And simple doesn't have loops, comes from this, right? Notice, for example, that I could add, so perhaps I'll put in a red color. If I added a new axiom like this, so what does this axiom says? Every time I give you three vertices, it is not true that X is adjacent to Y, Y is adjacent to Z, and Z is adjacent to X. So if I added this, axiom, what I get is theory of triangle free graphs.
So all your axioms are universal. Can you also handle other types of axioms?
You're anticipating my next thing. We're going to assume actually that the theory is universal because it's going to be very convenient to define densities. So, in fact, I'm going to assume theories are universal. What does that mean? This means that axioms are the form where every X, potentially a tuple, there's some form of defaults. And this, of course, needs to be quantifier free, otherwise, you can write anything like this.
There is no existential quantifier.
Yes, there's no existential. Universal means you only use universal quantifiers. Okay. Now, why is this important? This is important because if I have a model M of my theory, right? So here's M.
M was also the verb. M, sorry.
Yeah, M is some model. Say if you want, it's a graph or a triangle-free graph.
You call the structure M. I don't know why.
Okay. Well, it's because all the structures that I'm going to work with will be models of some theory. So I saved a step. Typically, you call it something else like K or something, but okay. So I have a model M, and imagine that I have some subset of vertices. Right? So here's the subset of vertices, U. Now I can consider the restriction of M to U, right? So M restricted to U, well, the vertex set of this is just going to be U, And each of the predicate symbols are just going to be the intersection with U. So you have the usual predicate symbol intersection with, so all the tuples that are completely contained there, right? So this is the endorsed structure, right? You take your model, you restrict your attention to here. So if my theory is universal, all of the axioms are of this form.
What is this P to the M?
P to the M is the relation, right? Remember, every time I have a predicate symbol, I have a set of tuples, right? So when I need to define a new structure, I need to say, what's the vertex set? It's going to be U. What's each of the relations? Well, the idea is that I want to restrict M to U. So I want to say, well, it's every tuple that's completely contained in U, right? So take the set of all tuples that were true and intersect with things that are completely contained in U, right? Now, notice that because all of our axioms are going to be of this form, this guy is a model. Right? Because
those substructures of models are models.
Exactly. And this is going to be very important because we are going to study these extremal combinatorics problems. And as we said, we had these notions of densities, right? So this allows us to define density of a model in another. Again, I guess you can define for arbitrary structures, but there's a very important property that will hold. So you can define density of a model in another, so this is density. So what this is saying is that, well, it's a probability that n, so probability over U, n restricted to U is isomorphic to M.
And U is the sign.
And here, yeah, U is uniformly at random. Subset of the n with size. Okay, so
At V of M?
what?
V of M?
V of n, the vertex set of
No, M.
Oh, yeah, this is a shorthand. Being lazy. Okay, so the idea is here's your n, you sample uniformly at random U, and you ask the question, is n restricted to U isomorphic to M? Right? That's the idea of this definition. Now, isomorphic, it is the notion that you expect. Two models are isomorphic if there's a function between them that's bijective and preserves relations and non-relations, right? So I guess, let's say F iso from M to N, or I should perhaps call it M1 to M2, use if F projection and if you take alpha is in some p to the m, if M1, if and only if F composed with alpha is in p to the m. For every alpha. For every b. Okay. So for graphs is the usual notion of isomorphism, right? It's a map that preserves edges and non-edges, right? But you could have more predicate symbols and you need to preserve every predicate symbol, every non-predicate symbol as well. Okay? So this is just saying, count the number of copies of M, number of isomorphic copies of M in N and normalize it, right? That's what this is saying, okay? Now, why do we need universal? Because technically you can define this for arbitrary structures. Well, this gives you a very important property, which is if you sum P of M n over all models of a certain size, so this is all models size n, diviso. If you do the sum, well, you're sampling this and you're asking, is this isomorphic to something, and summing over all possible things that can arise, because whatever you're sampling and you restrict is going to be a model of size n. So this sum needs to be 1. This is where we're actually using that as universal. And this is going to be very important later. Okay.
Models of size n is a countable set.
So here's where finite language comes, right? Because if you have a finite relational language and the vertex set is finite, then you have finitely many sets of tuples that you can pick. So it's finite, right? So each size n has a finite amount of models up to isomorphism.
Oh, I see. So it's not even, it's finite. It's not even countable.
It's not even countable. It's finite, and this is going to be somewhat important that it's finite. Now, if you're really interested in generalizations, you can get away with countable, but it's more annoying. You cannot get away with uncountable. But with countable, you can sort of get away, but you need to be very much more careful about what you're doing in later steps. But graphs is even better. You have a single predicate symbol. You're not even thinking about finitely many. And most of the applications in extremal combinatorics, you will have like 1 or 2 or 3 predicate symbols. But any finite number is okay. Okay, so we are interested in.
So there's a question. Can you handle something like permutations this way, or do you need to add something to be able to do this?
I could not understand. Can you repeat, please?
Yeah, so another structure where you have these limit objects are permutations, like you have permutants. Can you do permutants this way?
Oh, so permutations. Okay, so permutations a priori are a problem because if you're putting, I think I already raised, if you're just stating permutations as they are, a set of functions, right? So you either are going to put a function symbol, which I disallowed because we were working with relational languages, or you're going to try to state it as some sort of a group, and then you're going to have to use existential quantifiers. However, if you're interested about subpermutations, if you know what subpermutation is, you have a permutation, you can look at a certain set of vertices and just look at the relative order of that and say, well, the subpermutation that set of vertices spans is whichever permutation on that many vertices that have that relative order, right? So for example, you have 1, 3, 2, 4, there's a permutation. And if I want to look at the permutation spanned by these 3 vertices, this is going to be 2, 1, 3. Right? Because it's
So you encode it as a transitive tournament?
What?
So you encode the permutation as a transitive tournament?
As a what? As a class of?
Transitive tournament.
Oh, permanent.
Tournament. Like in sports.
What? Sorry, I can't hear the echo. It is. I can't.
The echo is problematic, but you can discuss permutations later if they are not automatically fitting this model.
What I was going to say is that if you only care about subpermutations, which is typically what you care about when you're studying extremal permutation theory, which deals with packing or forbidding subpermutations, then actually you can encode here as just 2 linear orders, the natural linear order and the linear orders given by the permutation. So that's how, for example, there's a lot of things of like algebras that apply to permutations, but you cannot do more fancy stuff with permutations in this vanilla case, like for example, study the number of cycles of a permutation. This is problematic. But you can study things like subpermutations with this theory. Any more questions before I proceed? Okay. So where were we? Okay, so we defined density, right? So now we're interested in studying what happens to these densities when this n guy, the guy on the right, is very, very large, right? And so what we want to say is that I want to somehow encode what is a large combinatorial object. And by combinatorial object, I mean, I have fixed some theory T, which I'm going to work, say graphs or triangle-free graphs. And I'm going to somehow think, what is a very large triangle-free graph, say? right? Now, you can try to think of it intuitively, right? And say, well, I could say to you, think of a very large clique. And if I say that, probably everyone understands what I mean, right? But what I'm actually saying is that what you're thinking of is for each n, there is a clique n, right? And if you want n to be larger, well, there's also another clique on that larger n, right? So actually, when you're thinking about large objects, what you're thinking of is some sort of sequence that for each size n, you have some object there. Now, of course, not any sequence should be thought of a single large object, because, for example, if I tell you, oh, think of a large graph such that if the size is even, it's a clique, if the size is odd, is an empty graph. Okay, that is a perfectly valid construction, but you probably don't think of this as a single object, but rather two objects mixed together, right? So the idea here is that we're going to define a notion that kind of uniformizes and says, this is what actually means to have a large object, which is that of convergence. So we're going to say that some sequence is convergent so I guess convergence of models. Well, the first thing is just a technicality because we want to think that these guys are growing in size, so that we're really encoding a large object.
So they are all satisfying the same.
Yes, there is an underlying theory that you have fixed. In all this talk, let's think that we have a fixed theory. If you want, think of graphs or triangle-free graphs, but it will work for any fixed theory, right? So it's convergent. To be completely formal, you would say convergent sequence of models of D, right? And etc., right? And the second thing that we're going to require is that for every model, there exists the limit of the densities of that model in the sequence, right? Now, this is saying that the sequence cannot look too crazy, right? At least if you try to sample things inside it, it behaves kind of in a way that converges to something. Another way of seeing is a more pragmatic way of seeing is that saying, well, I want to define some sort of convergence, right? And convergence of arbitrary combinatorial objects, there is no way of really thinking about this. The only thing that really makes sense to think about convergence that's very easy is convergence of numbers, right? Which kinds of numbers I can compute in my sequence? Well, I can compute densities. So I might as well require every fixed density to be a convergent sequence of numbers. And that's a more pragmatic view of convergence. Right?
In the case of graphs, this would be like a weak, something a bit weaker than Benjamin Schramm.
Then what?
You should think way before Benjamin Schramm. The other theory of limits of graphs or combinatorial objects is the theory of Lovász and its collaborators, which is called graph limit. And that is the main, there is no algebra and there is no, it's just reducing the notion of a limit or a convergent sequence from objects to numbers in exactly this way. You just want the density of any fixed, structure that you see to converge. Yeah.
I will say, however, that Benjamin Schramm can also be seen kind of like this, but not in the setup that we're doing here. But you can still see Benjamin Schramm as you compute densities of something and you require that to converge for everything that you do.
It came later, well, maybe not came later, but it's more complicated, and this is very related to
on like spectral densities of subgraphs.
Well, I'm less familiar with all the equivalences of Benjamin Schramm, but there's a way that you can do is that you sample a vertex uniformly at random, look at the neighborhood of a certain radius, and ask these to be convergent distributions. Yeah. You can think of this as being density of a labeled connected graph. A graph with a special vertex that's connected and has diameter at most r or whatever, right? Or a radius from the labeled vertex at most r. And you're computing densities of these and requiring those to converge. So it can be seen something similar to this, but it's not in the setup.
That's exactly what my motivation for asking that.
Yes.
So
It's not in the setup because, you know, this setup is not sampling the same way, right? But there is a way of encoding everything under a single umbrella. It's called the theory of FO limits, which is not in that picture. But since it has been asked, I will put this here. So FO limits. So this is by Nisifril. Oh, his name is a problem. There's a bunch of check signs that I don't know where they go, and those some of them in this.
The theory is talking about makes sense only for dense model.
Yes, but this FO limit thing, actually, you can encode everything, both graph limits, graphons and flag algebras, and this Benjamin Shroud under the single umbrella. FO here stands for first order. It's the same first order of relational languages that we're using here. You can encode everything under a single umbrella. But let me point out that the sparse case is much more complicated. Even basic questions are still open. Okay, so this is the notion of convergence. So you want to really think that this is the dense case, because otherwise there will still be convergent sequences, but they will all converge to a trivial object. So that is, okay, so that's it. So the question right here, we just defined convergence. So the question that you might ask is, what is the limit? Right, I just defined convergence of a bunch of objects. So what is the limit of this sequence that I'm calling convergence? Convergence, right? So flag algebras is going to answer this. It's going to do it in a minimalist way. So what is the minimalist answer? Well, what is the least amount of information that I need to encode if I want to talk about convergent sequence of models? Well, I have these limits, right? Might as well encode them, right? So let's define a function from the models to 0, 1. And definition is going to be phi of m. It's going to be the limit. So here what I'm saying is that, you know, n converges to this phi. That's what I want to define. It's going to be, I'm going to say n converges to this phi if phi is this function. It's the function. It's encoding all these densities, right? Okay. So that's the definition of the limit, quote unquote. But the question is, okay, so first, let's look at what is this? This is, so what elements of, so the set of functions that are of this form is 0, 1 to the m. What elements of this are limits? That's the big question, right? Not every element of this cube is a limit, right? For example, if I told you here's a convergent sequence and the edge density goes to 1, you know that the triangle density doesn't go to 0, right? So in particular, there's a relation between edge density and triangle density that forces if edge density is 1, triangle density cannot be 0, right? Now, let us point out your comment earlier, right? The set of any model, the set of models of size n up to isomorphism is finite. If you take the union over all n, this guy is at least countable. Right? That's going to be very important because if you think of each of these models, right, you can think of them as this weird functional. Right? This weird functional sits on this cube. Right? And when you look at this definition here, convergence is just convergence in this cube in product topology, right? So convergence in product topology. Okay, modulo the size is going to infinity, of course, right? Now, the important thing is that this product topology is compact metrizable. Right, so it's just a cube with countably many coordinates. So it's compact, and there's a metric. It's not a natural metric, but there's a metric. On this topology. And because it's compact metrizable, in particular, any sequence, as long as the sizes are increasing, any sequence at least has convergent subsequences, right? So even if you're trying to study a sequence that's a priori not convergent, this will be fine because you can say, well, the space is compact, so pass through a convergent subsequence. As long as you can study all possible limits of all possible convergent subsequences, you can describe what the sequence was initially. Okay? So, all right, so let's go back to this question. What elements of this cube are actually limits? Right, as we said, in graphs, if the edge density is 1, then the triangle density cannot be 0. More specifically, does anyone have any idea what the triangle density needs to be? If the edge density is 1, goes to 1, what is the triangle density?
It's a cube of
What?
it is the density cube.
No, it needs to be if the edge density
One
is
cube
1.
is
Yeah.
one cube
It's
is
going to
one.
be, it's also going to be 1, right? But in general, it is not necessarily true that the triangle density is the cube of the edge density, because say take the complete bipartite graph, arbitrarily large, doesn't have any triangles, but it has positive edge density, right? So the first kind of relations that we're going to study, there's this interesting thing that they say about representation theory, which is the human mind is really only able to understand linear stuff. So representation theory, you turn something into linear because that we can understand. So the first kind of relations we're going to try to understand is linear relations. And this is given by what's called the chain rule. And the chain rule is completely in the finite. So here's the statement of the chain rule. Right, so of course there's a condition here, which is n. Okay, so if I want to look at n, sample something of size m, and ask whether it's isomorphic to m, I could do this in 2 steps. I could first sample something of an intermediate size, ask it to be isomorphic to some n tilde, and inside n tilde sample something of size m, and ask it to be isomorphic to m, and sum over all possible choices of n tilde, right? What's going on is that here's the picture, so here's n, and then you sample something of an intermediate size n, and you ask, is this guy isomorphic to n tilde? And then inside here, you sample something of size m, and you ask, is this guy isomorphic to m? And then you sum over all choices of n tilde, right? And this is all, right? This is a double counting argument, right?
This is the flags.
What?
These are the flags in the flag.
Almost.
Okay.
Later they will be the flags, but at this point I'm doing only for models. Yes. Okay. But notice that if I have my sequence of models going to phi, I can plug them in here, right? Just plug these here, right? And what I will conclude is that phi of m, right? If I take the limit, I'm going to conclude that phi of m is equal to the sum of n tilde in mn, em n tilde, phi of n tilde. This is giving me some linear relation between densities of between the different coordinates of my phi, right? So, for example, let's revisit a calculation that we've done before. Phi of an edge for a graph is equal to phi of, I guess, is equal to, well, you can see 3 vertices, compute phi, this contributes 0. You can see this contributes 1/3. You can see the 2f, this contributes 2/3, and you can see the triangle, and that contributes 1. Right? In particular, this is a relation that comes from that. And we actually use that in Manto's theorem, right? So, okay. So what is the easiest way of encoding satisfaction of linear relations is to come up with some vector space and require something to be in the kernel of a function, right? So what we're going to do is we're going to say,
Had we used that, we wouldn't need the little o one.
well, in this one, there's no little o of 1. Yes, in this one, there's no error. Later on, there will be a problem. You know, in the same place that there was an error, which was in the product, right? That is the one that actually has an error that will disappear in the limit. Okay, so let's encode these linear relations. So how do we do that? We say, well, let's extend phi linearly to a function that goes from formal linear combinations of models to, well, I guess real numbers. And well, it's the natural extension, right? So if I give you some formal linear combination like this, you're going to just say, well, this is the same combination of the values of phi. Right? So I'm using notation here and using the same letter for the extension as phi, right? And because chain rule says this, you can say, well, let's define kappa to be the span inside the space of formal linear combinations, the span of all expressions that look like this, m minus sum of n tilde in mn, p m n tilde, n tilde. So these are some expressions. So n tilde is any model, and m is any model, and n needs to be at least m. And what this is saying is that this chain rule, what it's saying is that everything in this span, phi needs to map to 0, right? So this means that k is contained in the kernel of phi, right? So in other words, I can think of phi as a function that goes from a to the real numbers, where a is just this quotient. It's a perfectly valid vector space, and I know that whatever limit I'm going to produce, if I extend it linearly, it actually is a linear function from this a, which is just this quotient. Okay.
Could you repeat how you embed models into a linear space, into a vector space? You have a span of an algebraic
This is
expression,
formal linear combinations, right?
but of numbers, because the phase are numbers.
No, formal linear combinations of models, right? So for each, you can think of this as that for each model, there's a number, a coefficient, right? So I'm going to extend this function to be able to evaluate in these formal linear combinations. And the way that I'm going to extend this, well, you give me the coefficients of each model, you take the sum over all possible models of the coefficient times what was the value of phi. Right?
And then you have a span of something without a field.
Oh, so now here I'm working over these formal linear combinations. So this is a formal linear combination of models, right? Because it's 1 times this model minus a sum of some coefficients times other models, right? So this is a perfectly valid vector space. So I can take all possible elements of this vector space that look like this and take their span, right? And then what chain rule is saying is that when I compute phi, say on these basis elements of the span, well, it's not the basis, but okay, it generates by them, phi on each of these is 0, right? Because you compute phi on n and compute phi on n tilde, you get exactly this expression, which is, okay, you get this expression, which is 0, right? So this means that each of the things that are generating are in the kernel, therefore the whole space is in the kernel. So that is contained in the kernel of phi. Right? In other words, I could factor kappa, and phi is still a well-defined function, and that's what we're doing. Okay, so this is what's going to become the algebra, but if you know algebra is missing a product, right? And that's the next step. We're going to study products. So to study products, we need a different definition, which is the joint density of M1, M2, in a certain target model. Let's call it N. Okay, so what is this? This is going to be the probability over U1, U2 that N restricted to UI is isomorphic to MI over each. And here, U1, U2 are picked uniformly at random. Conditioned. On well, you want the sizes to be correct, but now you're going to do something slightly weird, which is you're going to say, I will also require that they are disjoint. Okay. Now, there is not much intuition that I can put here is you need to do this because this is the thing that works. Because if you allow disjointness, even though intuitively you are capturing the product more precisely, you're not going to get the property that we want next, which is
since M1 and M2 are fixed size,
yes, this will play a big
role. This happens anyway.
Yeah, the idea, as Avi's mentioned, and this is going to come up later, is that okay, maybe you are really complaining that these guys are disjoint and they don't really encode the product. And the product should just be, this. But in fact, because if you think that n is very large, the probability that these guys are disjoint is almost 1. And more precisely, you can say that this is the difference between these two guys is 1 over big O of n, and here big O is hiding things that depend on M1 and M2, but remember the notion of convergence is for each fixed M that is convergent, any finite number will also have that, so you can fix them in advance and you have a uniform bound, right? For every fixed M1, M2 gives you a uniform bound based on the size of n. Okay, now the neat thing about this is that you can equip A with the linear product. And the linear product is given like this. M1 times M2 is equal to sum over n of n. And here, I'm requiring that n is at least sum of sizes. Okay, so you equip this with the linear product, and it becomes commutative or object with unit.
But on the left hand side, you don't have little n.
Yeah, no, it's a linear. You want to express it in the linear combination of the mode. You want to be in order.
So I'm going to define a bilinear product. It's bilinear. It's enough to define it on something that generates the space. I'm going to define it in this way. What generates the space? Each of the models do. If you take the family of models, generates the space. So I'm going to describe to you what is M1 times M2. M1 times M2 is this formal linear combination of models. Right? You take these numbers.
But for which little n?
Yes.
Little n here.
N is anything that satisfies that. But then you can say, well, but I could pick a different one. It will give you the same thing.
Okay,
The difference will be in the.
Okay, so you're saying it's going to give you the same thing?
Yes, well, the difference will be in kernel.
In the kernel. The difference would be in the kernel.
Yes. So you have to prove this. I'm not going to prove it's a boring calculation. But you can prove that this is well defined. You know, where you could have freedom actually lands on kappa, so you don't, it gives you the same result. The same way the unit, again, I'm saying the unit is you sum every model of a fixed size. What size? It doesn't matter. It gives you the same thing. The difference of this with two different ends is in kappa.
Yeah, so it's the same little n for the addition, product, and unit. It is the same.
No. You pick any n satisfying this. And this definition doesn't depend on your choice of n. That's what I'm saying.
Okay, and the little n in the addition is not fixed.
This again is saying kappa by definition is the span of all expressions that look like this for any fixed n that is larger than this. And exactly because kappa is defined like this is because when I think of this product from going from A cross A to A, if you pick a different n, you get a different expression. Take their subtraction. It's going to be in kappa. That's what I'm saying, right? So in A, it's well defined.
So you have layers for each little n, but all of these layers are included in kappa.
Yes.
So kappa has.
Yes. Kappa is saying, given something at a certain level, how do you express it as a linear combination of something of a larger level?
Yeah. And then,
it's not necessarily true that you can go down, but you can always go up, right?
By the chain rule.
Yeah, by the chain rule. Yeah, the motivation for kappa, remember, we know that phi will satisfy that. Which is intuitively what we were doing on Mendel's theorem, right? You have, if you want to compute the density of an edge, you can compute that based off of some linear combinations of these densities of things of size 3. Right? Okay, so that gives us the algebra. And notice that, I guess I need. I think I need one more chain rule. There is a version of chain rule that is, I guess I shouldn't have raised the normal chain rule. It's too late now. There's a version of chain rule that holds for this weird density, this joint density here. So here's chain rule 2. Which says that if you want to compute PM1, M2 in N, well, this is the same as computing. Take some N, tilde, compute this guy in N tilde, and then compute N tilde in N. Okay.
only the n larger than the sum one.
Okay.
Are you adding these linear relations to your algebra?
No, because, well, no, but also yes. We'll see how these are added. The reason is like this. Let's look at what happened, right? So we have some sequence n converging to 5. Okay, so what happens if I plug in here? Right? If I plug in here and on this side, right? Well, if I take the limit, what is this expression? Well, this expression is going to be exactly phi of m1 times m2, right? That's exactly the definition of product there. And over here, well, okay, this one I don't know what it is, but at least this inequality here says that this guy, at least in limit, it tends to the same thing that the product goes, right? Because if you fix M1, M2, then these two things are very close together, right? And this limit, I know what it is because this is just phi M1, phi M2. So you see, product becomes product. So what this is saying is that phi is an algebra, our algebra, homomorphism.
No negative way.
Yes, let me just, before I get there, actually, there's one thing more that I need to check. Phi needs to map 1 to 1, right? So what is phi of 1? Well, phi of 1 is the sum. Remember, 1 is the sum of all models of a fixed size. So this is just this sum, right? Phi is linear, so this I can put sum outside. But now this is the sum of all densities of a certain size. So this is certainly 1, right? Because it's true in the finite. Right? So this is our algebra homomorphism, but as Avi mentioned, it's not any algebra homomorphism, right? There's some algebra homomorphisms that potentially assign negative values to models. Phi doesn't do that. So in fact, you can define this hom plus R. This is the set of all homomorphisms such that for every model, phi of m is greater or equal to 0, right? So we certainly know that anything that comes from limits is in this set, right? Because densities of a model, not a combination of models, a model need to be, in fact, a number between 0 and 1. Okay, you could say I could plug this between 0 and 1, but you can check that just because the sum of them is 1 and they're all non-negative, they also need to be at most 1. So that condition is enough. Okay, so here's the big theorem of like algebras. So hom plus A R is exactly the set of limits. So a couple of explanations. Typically put Lovász and Szegedi here because this was indirectly done in the graph-on theory for graphs. Sasha himself puts in his paper this reference as well. So we also partially credit Lovász and Szegedi for doing this first for graphs, but in general, it was done by Razborov. And by exactly the set of limits, what's missing here is the converse, right? We proved that any limit is actually an element of the set. Let's prove that any element of the set is a limit of some convergent sequence. Okay, so let's see that. Okay, so proof. And I'm only going to prove the side that's missing. So, okay, so we have this phi, right? In this homomorphism, whatever it is. And we need to come up with a sequence, right? Okay, what is this phi? Well, this phi is a list of numbers, right? And what do we know about that? Well, we know something very silly, which is every model has non-zero value, right? It has non-negative value, right? So every time you see a bunch of things that have positive value, there's one thing that you should try, which is use them as a probability distribution, right? So what we're going to do is we're going to say sample and n according to probability of n is equal to n, well, it's phi n. Now we should check that these things add up to 1, but indeed they do, right? Because of this, right? If you sum everything of a certain size, this is equal to 1. It's an algebra homomorphism, right? Because that is the one of the algebra.
So what you are telling us is you are going to generate the elements of the sequence which will converge to this limit probabilistically.
Yes. So what I'm going to do is I'm going to
Each
produce,
element you are producing this way.
yes, I'm sampling and I'm going to produce a random sequence, and we'll see, but I will prove that with good probability, this will converge to the correct thing, right? So if it's going to be the correct thing, I might as well, one thing that needs to hold is at least in expectation, it needs to be correct. So let's see what happens to the expectation. And this is actually easy to do, right? So if I do this expectation, well, just the definition of expectation, this is the sum over all n's, mn, of p, m, n, phi of n, right? But phi is linear. So phi comes out. And now I can use the kernel to say that this is just phi of n. This is just chain, right? Phi satisfies that the difference of this needs to be mapped to 0, right? So at least in expectation, it is fine, right? The densities are indeed converging to the correct thing in expectation. So if the things are correct in expectation, so we need to prove a concentration, right? That's what we need to do next. So let's compute the variance. Because I want to eventually apply some sort of Borel-Cantelli, right? So I want to say, you know, apply Chebyshev, this bounds deviation, and then you want to say it's summable, and then Borel-Cantelli will give you convergence. So you need to compute variance. So, okay, what is variance? Well, variance is expectation of Pn squared minus, I already computed the expectation. This is phi m squared, right? Well, let's open up the expectation. This gives me sum over n mn squared times phi of n minus, well, phi is a algebra homomorphism. In particular, it respects products, so I can put the product inside, right? And now I know how to compute products. That's that definition there. And I'm going to put it in the same sum. So actually, I'm going to factor this out, and I'm going to say this is minus E m again, n I of n. Right? That's just the definition of product. Well, but now look at this. If m is fixed, then this is bounded, right? So the variance, whatever it is at most 1 over O of m, I guess. Well, O of the size of n, which is n. There's an m hidden here. Well, okay, granted, this is at most that, but when you sum this is 1. Okay, right? We're in trouble, right? Because we want it to be summable. This is not summable. It's 1 over n. Okay, it's not summable. Let's make it summable. And the way to make it summable is by cheating, which is say, okay, let's define n tilde, the n squared. And now it's summable, right? So now variance in tilde is at most 1 over O n squared, right? So then, then the rest is standard, right? So you say, okay, this makes the probability that the minus phi of m is larger than epsilon, that's less or equal than the variance times epsilon. squared. There's an epsilon squared, whatever, it doesn't matter. I don't remember if there's an epsilon squared. And then for alpha tally, gives that with probability 1, you have that P M tilde converges to phi M. Now, because it's with probability 1 and there's only countably many models, I might as well put for every fixed model this holds, right? Because it fails with probability 0, and there's countably many things that can fail, so it still fails with probability 0 with the for all, right? So then you're done, because this is some random sequence that with probability 1 converges to the correct, right? Okay. Any questions about this proof? This is a very, very, very beautiful proof. Very simple proof, but very, very cute. Now, you might be wondering if this cheating can be fixed. It can. You can actually produce a sequence that has a model on each side, but the argument is a little bit more complicated, and it kind of involves a little bit of semantics. So tune in next week, I guess. Talk about that. Perhaps. Okay, so I guess I erased Mandel's proof, Mandel's theorem proof. Okay, so if you remember the proof of Mandel's theorem, everything that we talked about so far, well, some things have already appeared, right? Computation of edges, what we're actually doing is we were doing computations in this algebra. That's what we're doing. But at some point, we did this weird computation of things like this, right? And this is not exactly captured so far, right? So that's where the actual flag part comes in. So to capture these kinds of things, you need to use these flags. And to talk about flags, I need to talk about types. So type is just a model sigma with, it's a very special type of model. The vertex set is going to be some brackets L. So this is just 1 through L.
With all the formalities here, maybe just say here, we want, until now, all objects were unlabeled. Now we want to label some.
Yes, that's what I was going to say. A flag is going to be a partially labeled model. So flag. Or more specifically, a sigma flag, a partially labeled model. Labels induce sigma. So the idea is that, here's your model, and there's some part that you're fixing a labeling, and it looks like sigma, right? So again, when we did Mantel's theorem, we did computations like this, right? So we computed something that there was the special vertex, right? So the way that I want to encode is not put V there, but rather put a label, say 1, right? And there were other things that was this, and we say 1 here, etc., right? But a priori, I could even label more things than just a single vertex, right? And here, I mean, I'm saying that all these flags, they are sort of different because I don't want to put in the same bag a flag that looks perhaps like this. This flag should probably not be put in the same bag as a flag that looks like this, because the labeled part of these guys are different. Another thing that is useful to bear in mind is that isomorphism flags are required to preserve labels. So, for example, this flag is certainly isomorphic to a flag that looks like this, but is not isomorphic to this flag because the label of this flag is in the wrong place. But you know, I guess this flag is isomorphic to this. Just the full range of examples. Right.
Labeled by Q.
What?
So the labeled by 1 is labeled by 1 isomorphic to labeled by Q.
Oh, by labeled because it needs to be sigma.
No,
sigma
he's
is always
asking, suppose you replace in, you have two isomorphic, the two left guys in your example, but you replace 1 by 2.
So the thing is that because it's a sigma flag, it's going to be a pair where this is a model and this theta goes from brackets L to V of M and is an iso sigma and its image. So M restricted to image. So it doesn't make sense to say labeled only by 2 because it needs to come from brackets L for the L corresponding to your type, right? So you can have only labels 1 up to some number, and whatever the labeling is, it needs to span the type that you're looking at. So here the type is 1 and 2 with an edge. Here the type is 1 and 2 without an edge. These are different types. This is a sigma 1 flag and this is a sigma 2 flag.
Yeah, but if you had, just the two left examples, this,
yes.
yeah, this and this, if you, in one of them, replace the 1 by a 2, there will not be isomorphic. Just name 1, replace it by a 2.
No, but if you replace by a 2, that violates the condition of flags.
Okay, so you don't even compare things
Yes.
that are different types. Good.
But no, what I'm saying is another thing. There does not exist something that you only use label 2, because the labels are required to be 1 up to L.
All the
So you
flags
cannot omit the label.
all need to appear.
Good. All of the labels have to appear in the.
Yes, but I guess it's a good point, right? So you could say, well, I could have a more complicated example where you would say, you take something that looks like 1, 2, 3, all of them are labeled. And perhaps, I don't know, perhaps there's another point that's not labeled, right? And if I look at something that looks similar, but not exactly, and say there's 1, but the 2 is here, and there's 3.
They are not isomorphic.
These are flags, but the types are different, right? Because this is a type that is 1, 2, 3, and its path has edges between 1 and 2, 2 and 3, but not between 1 and 3. And here's not the same thing between the labels. So the types of these flags are different. So you stop even before asking whether these things are isomorphic, because they are not even sigma flags for the same sigma. Okay.
So Leo, before moving on to flags, like the first example that you showed us, is it possible to show it without flags, the flags machinery, just using positivity of squares on the algebra?
I don't think so.
I mean, it seems that already you can prove some nice theorems only using.
It depends on what you mean by. It depends on what you mean by you can prove it, because you can, using only positive elements, you can certainly prove bounds that approach the correct value, because you can just expand into larger and larger sizes.
Yeah, but like a compact proof that does not go
A
to
finite
larger
proof, I don't think that mental theorem you can do without using flags. I don't think so.
Is there any non-trivial thing you can get without? I mean, it's already like, even without the flag, it seems like, it should span some nice results.
I think very few things in graph theory, interesting similar graph theory.
I was going to say, it depends on the definition of trivial, because I would argue that anything that you can do without using flags is by definition trivial, because you're just saying, oh, you express this as a square of something very simple, right? Something that you don't use times. But then you might argue that this is not necessarily trivial. Okay, but
there are a lot of things you can, I mean, this is in the realm of, real algebraic geometry. You have a bunch of inequalities, right? I mean, this, where this lives is about a bunch of inequalities on a given structure, and you are trying to infer from it another inequality.
Sure, sure.
That's where it lives. In this realm, you don't have to use flags. We know there are lots of results, lots of about all sorts of structures, all sorts of systems of polynomial. So it's not like you cannot prove anything without flags. It's just the questions that I think arise in extremal combinatorics.
Yeah, no, this answers my question.
But I wonder, there is a huge thing you can do just with.
But I don't see any a priori reason why without the flags you would not be able to reach non-trivial things. I don't know what a non-trivial thing is, right? I'm just like, there is no intuitive reason.
About extremal theoretic problems to convince yourself.
Yeah, okay, fair enough.
Okay,
so you need to look at the neighbors of particular.
No, this answers my question. Okay.
So now here's I'm going to not do the next step and just say everything far holds for sigma flags. So you fix a type sigma. So okay, you fix a theory. Inside this theory, you fix a type, and then you consider sigma flags. And for example, you can define densities of flags, right? P, F prime, by saying, well, this is the probability that F prime restricted to U is isomorphic to F. Probability is over U. U is required to have size equal to F. And well, this is a technicality that you want to say U certainly contains the labeled part. So here's your sigma part, here's your F prime. And what you're sampling is actually a set that is required to contain the sigma part, and you're asking whether this guy is isomorphic to F. That allows you to define everything that we have defined so far, and you have, again, that home plus a sigma. Now, this is what we use to indicate that you're using type sigma, is the set of limits of convergent sequences of sigma flags. Another way that you can think of is that whatever we were doing before, we're just doing a sigma flag where the type was trivial, has no labels at all.
Before you define kappa, using a summation over all models and then the chain rule.
Yes, now the summation is going to be over all flags. I can write
sigma flags for this sigma, right?
Yes, sigma is fixed. So you fix your sigma, and kappa sigma, which is exactly what you're going to factor by, is you're going to write like this. And kappa sigma, you're going to say, take a flag, subtract the sum over all flags of a fixed size, P of F in F tilde times F tilde. Take all possible choices like this and take the span. That gives you kappa sigma.
So we're not actually summing over just models, we're summing over permutations of the labels too, in some sense, right? Because like you allow isomorphisms.
You're summing over all sigma flags. So the sigma part is not permuted, if that's what you're wanting.
Yeah, but I meant like maybe two different models could have different labelings that induce the same sigma.
That's the theta. Yeah, you have a flag is M and theta, and in theta.
Yeah, well, when I say sigma flags, it means that the labeling must induce sigma. So if I'm saying convergent sequence of sigma flags, everything, the labeled part needs to induce sigma, but the unlabeled part can be anything.
What I meant, just to get it, that we're summing over all models and over all labels that are consistent with sigma, right?
Yes, but up to isomorphism of flags.
You're like modding out the isomorphism in some sense?
Yes, yeah, when I write, I guess I didn't say this, but I did say isomorphisms of flags are required to preserve labels, and this guy is the set of sigma flags up to isomorphism. in the same way that we did for models, right? But now the notion of isomorphism requires preserving labels. Maybe I can do a presentation. They're in the same page. They tend to become longer when you are working with flags. So I'll do a very simple one. So for example, say, well, let's look at this. This, if I apply the kernel and I try to expand it into 3 parts, I can say, well, I can see, this, you can see this, this you can have 1/2, then you can see this. Well, I should write this. This is going to contribute 1, and you can see this. 1/2, and then you can see, and everything else contributes 0. There are things, other things here, but they also contribute 0. Okay, so I'm missing a bunch of flags. Like first, I'm missing something that looks like this. I'm missing something that looks like this, but they all contribute 0 to this. Right? So this is one. So I guess the subtraction is in the kernel of this type 1. One is type that has a single vertex. Okay.
You mind? Can I go back to my question? Just
yes.
So in the example you gave us, you looked at the square of of like
in the same
edge
way,
and non-edge. Can you convince us that this cannot be expressed without the flag, this quantity? So like the quantity saying that the average degree, that most degrees are very close to n/2, right? Can you convince us that this cannot be expressed by just
well, it depends
at
on what you mean by not expressed, because the next topic is going to say, so if you want to just prove that the average degree is equal to 1/2 everywhere.
No, not average degree, right? What
No,
you said
sorry,
is that
I said average, but I didn't. If you want to express the fact that the degree is equal to 1/2 everywhere, except for small errors, then you can write it using flags, but we will see a calculation that rewrites it without flags and says, this is equivalent to saying this particular combination of models.
okay, so you can't
0.
Okay.
But you use flags and
Yes.
then you remove them
Yes.
by everything.
That's the topic of, that's the next topic, which is the averaging operator. Remember in the Mentos theorem proof, at some point we said, let's average.
Yeah. Okay, now I get it. Yeah. Okay.
You should have in the back of your mind Cauchy Schwarz.
Yeah. You cannot do Cauchy Schwarz without first fixing the vertex.
Yes, good.
Okay. Now I.
So I get, how am I for time? Because I think I have 5 minutes. I don't know.
Maybe finish with the averaging operator. I think it's will conclude nicely.
Well, it will be a little bit disappointing because I'll define the average operator and I'm going to define something called extension, but it will look a little bit mysterious for now. So I guess I'll end on a cliffhanger. So let's talk about this averaging operator. And we're going to also talk about sigma extensions. So if you recall what we did on Mentos theorem, at some point we said, well, we fix a vertex, right? And then we did this computation in this flag algebra, but of the type 1 that has this special vertex fixed. And then at some point we said, let's average over the choice of V, right? So this is what is going on there is based off of sigma extensions, but to explain sigma extensions, I will need the averaging operator. But let's start with sigma extensions and just with the intuition of what it says. The sigma extension, what is going to be is like this. Imagine that I give you this large phi, right? So phi is a limit object, but you can think that is a very large object, right? So here's phi. picture, right? Now, let's assume for a second that if I look at a certain type and I compute the density, this is positive, right? Okay. Now, if the density is positive and this is a large object, I could sample uniformly at random a copy of this object, right? So I could sample sigma, right? Chosen uniformly at random. And because phi is a large object, what do I have now? I have a large sigma flag, a random large sigma flag, because it's random because I chose the labeling part at random. So sigma extensions are going to encode exactly this, right? So it's the element or the random element of limits of flags. So this is a sigma R encoding labeling copy sigma at random in phi. Okay, so this is the intuition. The definition is that it's a random element, say phi sigma. So all that I'm going to require is that in expectation, everything works as I would like, which is if I try to compute expected value of the density of a flag, what I see is some specific number. This specific number, whatever is happening on the right-hand side is based off of the averaging operator, which I'm going to say, right? And the averaging operator is that weird bracket that I wrote. So if I give you some flag f and theta, so this, the averaging operator of f is some number, q sigma of f times m, and this guy, say what this is this number, but notice first that this guy is some element in the normal algebra, right? So this is algebra of models, or flag algebra of models. Right, so it's a combination of models, not of flags, so it's going down. And this guy is probability over choice of eta that m eta is isomorphic to f, where eta is some injection uniformly at random. Injection. Uniformly. So what I'm doing here is I'm saying, well, look at my flag f, forget the labeling, label anything at random. What is the probability that you see this picture? Right? That is what this number is. Okay. So we actually computed some of these these averaging operators before. We just didn't notice that we were computing them. But what was going on is that for example, let's try to compute the averaging operator of this guy. One, well, whatever is going to be this model, right? Times some number. What is the number? Is the probability that labeling this uniformly at random, you see this, which is 1/3, right? So when we're doing averaging over vertices, what we were doing was we were applying this averaging operator. By the way, you want to think that this is actually a linear operator from a sigma to a, right? So I just defined them on flags, but extend it linearly to this space. And again, you have to check that if you change the flags by things in the kernel, it also will change the result by things in the kernel. So no, this is not a algebra homomorphism. It does not preserve products. It's linear, but it does not preserve products, right? But this guy here is saying, if you want to compute the expected value, there's actually a way of computing what they should be based off of the densities of the original thing, right? So what is going on here is actually a double counting because here you're saying there's this large object, you're sampling uniformly at random sigma there, and then you're asking, if I complete it with some other vertices, what's the probability that is isomorphic to F? And on the right-hand side, forget about the denominator. What you're saying is that, you know, phi is going to be computed on the underlying model of the flag. So you forget the labels of the flag and try to find a copy of that model. And then inside there, you try to label so that you see sigma, right? So it's the double counting happening on the other order, right? Okay, so should I perhaps, should I end here? It's cliffhanger, or do I have time to prove that this is actually?
Don't prove anything more. I think.
What?
Don't prove anything. You can state something, but that's not proof.
Okay, so I guess instead of proving, so I guess next time I will prove that this indeed is encoding what we want to encode. But I will finish by trying to give an idea of what was going on Mantel's theorem, right? So what was happening is that we actually want to say you're interested in what's called the semantic cone. The semantic cone. So these are the elements that are non-negative in the algebra. So this means that if I give you some limit, then it's non-negative. So what was Mantel theorem trying to prove? Mantel theorem was trying to prove, or at least the hard direction of Mantel theorem, it was trying to say that if you take the edge, or I guess if you take 1/2 minus the edge, then this is in the semantic cone. That's of the normal algebra, right? I guess you can also, if you want, you can define as usual. If F minus G is in the semantic cone, I'm going to say that F is greater or equal to G. So in other words, what Mantel's theorem was trying to prove is that edge is less or equal than 1/2. And here you want to interpret, here's the 1/2 times the 1 of the algebra. That was what Mantel theorem was trying to prove, right? And what it was relying on is two things. First, there's a trivial subset of this cone, which is the ordinary cone. The ordinary cone is the set of things that look like this. So if I give you a sum of flags times the square of things, of course, this thing is non-negative, right? Because if I apply phi here, well, phi is linear, it goes inside the sum. Phi of a flag is non-negative, and phi of whatever square, the square goes outside, so it's also non-negative, right? So this is obviously a subset of the semantic cone. And the other part that Mantel's theorem was relying on is that this averaging operator actually preserves the order. So if you apply it to the semantic cone, this is contained in the semantic cone downstairs, right? So in other words, you give me a non-negative element, you average it, it's a non-negative element without labels, right? That's what it was saying. So the whole semi-definite method actually relies on this, because these kinds of things will correspond to some positive semi-definite matrix times some coefficients, and then you're just doing the same kind of proof of Mento's theorem that you say, take whatever was the density, add something that's a sum of squares essentially. So this only can increase. And then this changes some coefficients, and some negative coefficients knock down some coefficients that are high, take the maximum of the coefficients, and that's a bound, right? That's what was going on. And this is the semi-definite method, which I guess I can complete the proof. Next time I will prove this, which will go through by proving that these guys actually are encoding random choices of sigma in a large object. Okay.
Right. Questions? Yeah, so it didn't tell us if it's complete.
Yes, so
if it can prove anything that we want to prove.
Unfortunately, okay, so the semi-definite method will give you a family of semi-definite programs. It's an infinite family. You can prove that it converges, but it converges for trivial reasons. So it proves better and better bounds, and the limit, it actually reaches the value. But there's a result by Hatami and Noreen that says that.
So first, the answer is yes. It, in principle, can give you the true answer to any such.
Well, you can approximate.
Yeah, up to, you can approximate arbitrarily well just using this theory.
Yes,
the value of any extremal problem.
And as the previous question by Ronan, he said, in fact, you don't even need everything here, right? Because if you just use expansion into larger and larger objects, you would get that the approximation is going, right? But if you want to actually find it by some finite level, that actually, there's a result that says it's at least for the theory of graphs, is undecided. If you give me some f and you ask, is it a non-negative element? There's no algorithm that does this. So in particular, this also doesn't, right? At least for the theory of graphs. Some simpler theories, it's going to be decidable just because maybe the theory is trivial, but in general, you cannot hope that a finite level will do this because that would give an algorithm. No such thing exists.
No question. Well, I will make a comment, just that, this theory has proven, several outstanding conjectures in extremal combinatorics that were not accessible yet. Still, some of the big open problems are not solved by. So
and were they found by some kind of brute force search or not exactly brute force?
It is actually brute force. You write a semi-definite program and you say, here are some types. Here's the size of the expansion that I want to do. Try to find a positive semi-definite matrix and minimize.
So people did that and actually managed to.
And it gives you an upper bound. Every time you run your favorite solver, it gives you an upper bound. Now, granted, you typically cannot expand too large. Like for instance, if you're doing graphs, if you're doing expansion into graphs of size 7 or more, it's already becoming complicated because the number of graphs is getting large, and not only that, the number of flags is getting even larger. So you cannot go too far in this hierarchy.
7 is a lot, I mean.
Yes, it is a lot. There are several problems that people just didn't know how to solve, and you run this and you get a perfect tight bound. Now, of course, there's some, you have to be mindful about numerical errors, and you have to round, which is a whole different problem. But sometimes you can round and do these things because the semi-definite solver spits out something that maybe is not actually PSD, is almost PSD, and the bound it spits, maybe say in the Mento's case, maybe it's not 1/2, it's 0.50001, and you need to argue that. In the case of Mento's theorem, I gave you this.
You need to do theory except for the first famous case that was solved using this method is the generalization of Mantel's theorem to the question, okay, we want zero density of triangles, what's the maximum density of edges? But suppose I want the density of triangles, how large can the graph be? And he figured it out completely. It's a really weird
Yes, but let me point out that to solve that, you actually need, or at least the proof by Sasha uses also differential method, which I did not talk about.
So it's kind of a variational.
Yes,
over this.
so I can say a couple of words about differential method, which is, if you look at this hom plus, right, you can think of it as a subset of this cube, right? But you just put some linear constraints and some product constraints. So it's kind of like a variety sitting inside this, right? It's an infinite dimensional variety. And if it's an infinite dimensional variety, you can do variational arguments, right? You can say, morally, you can say, here is a function that I want to find a local optimal, because I actually want to find an optimal. So it's a local optimal. So I can do the gradient. Now, it's complicated because, you know, there's countably many restrictions, but you can kind of get around that by saying, okay, I don't really know what, there's infinitely many restrictions, but here's a direction that I know lies in the tangent space. And then you say, well, because this direction lies in the tangent space, my function, the gradient along that direction needs to be 0 if I'm a local optimal. Right? Assuming, you know, the domain is open, whatever, right? So that is kind of the idea of the differential method there. So Sasha uses both the semidefinite method and the differential method to solve the result of triangle density, if I'm not mistaken, if I remember correctly how the proof goes. But I'm not going to talk about the differential method because it's more complicated.
Any more? Last, thank you.